on to Lab 4, where we see some interesting questions. A professor is trying to see that if students would do better if they're taught RStudio versus Excel in their class. So what they do is they teach both softwares to their students, and then they give one quiz where the students are only allowed to use RStudio, and they give another quiz where they can only use Excel. So the situation is both students, or one, like every student gets two tests. Like when we are talking about using your flowcharts, are the samples paired? Imagine the class. Each person in the class gets two tests. It's the RStudio test as well as the Excel test. And so when they are comparing how they did, each student compares their result from RStudio test to their result with the Excel test. So here, are you performing tests on the same subjects, or are there natural pairings? In this case, the answer is yes. Okay, so here we now are seeing a paired situation. So what I did was I downloaded the file, and here now I've imported it into R. And our next step after saying that they're paired is to see if the difference of the pairs are normal. So we have to be really careful here. Originally, to find just if we had normality, we would just find the ad.test on one column and then the other. But that's not what we're looking for here. We're looking for the normality of the differences. So instead of saying ad.test on one column or the other, I'm going to do ad.test of one column minus the other column. Okay, so make sure that, of course, you've got the nor test package installed and loaded, and then you can run the test of normality on the difference. Okay, so here I got, in this case, that the normality p-value is very high. Okay, what does that mean? Here, the difference of paired looks like it's normal. Okay, so here the p-value is very large, so it looks like it is the difference between the samples is normal. So that means, yes, I'm going to go to a matched t-test. Okay, so you could run Levine's test if you wanted to, but there's not really any reason to. The only time that you really run Levine's test is when you've got a two-sample unpaired test to see if you've got Levine's. Here, we just said they're paired. The differences are normal, so we can go right to the the paired t-test or the matched pair test. And you can run that in the same way that you can run a two-sample t-test with equal variance or with unequal variance. So it's still the t.test command, one column, the other column. Make sure you have your sign in the alternative be the way that you would like it to be. So what we're trying to find out here is, sorry, I just need to get to the right question. What we're trying to see is if the average scores on RStudio were greater than the average scores on Excel. So here, if I list RStudio first, then the sign should be the greater than sign, and the Excel would be the second. So here I've listed RStudio first, then I've listed Excel second, and then I made the sign greater. We're trying to see if they're better than each other. One thing about writing the hypothesis, you should be careful. If we're actually pairing the hypothesis up, we shouldn't write it as two separate means. We should write it as one mean where we're talking about the difference between the two groups, because we're not talking about two groups anymore. We've now taken the difference between the two separate groups and now found one group of differences. So this is the mean of the mu of differences. So here the sign should be greater than, but it should be mu sub the difference is greater than, you can see here, just 0, to see if RStudio, the average RStudio is doing better than the average of Excel. Okay, so here the alternative is the greater than sign, mu is 0. Here, one huge difference is saying that the data is paired. So if you don't say that the data is paired, you're going to get one of these two sample t-tests, not this matched pairs test. So to get the matched pairs test, you need to set paired equal to true. Then you can say conf level is equal to whatever level of significant confidence you want. And it really doesn't matter if you put variance equal or variance equal to true or variance equal to false. This is completely ignored when you are just doing a paired t-test. So then you can run a paired t-test. And here's the test statistic for the paired t-test. Here's the degree of freedom. And here is the p-value. In this case, the p-value is quite small. So the p-value is small, so I'm going to reject the null hypothesis, which is the less than or equal to sign, in favor of the greater than sign. So what this is saying is it looks like the mean of the differences when you take RStudio minus Excel is actually greater than 0. What does that imply? Well, it implies that the average of the RStudio quiz was higher than the average of the not high the Excel group. Okay, so here just going through the actual what did I have to put in using the technology, what did we need to do? We needed to find if the data had pairings, and then we needed to find if the difference of pairings was normal. We didn't have to run Levine's test. We didn't have to do anything else. All we had to do, just going back to the flow chart, we decided they were paired, and then we decided they were normal. The differences were normal. That's what we had. Those are the two things that we had to do. Therefore, I ran a paired t-test here. Mu's should be here mu sub differences because they're paired, not mu A versus mu B. I'm actually combining the groups. I found the test statistic, okay, for the matched paired test, and I also found the p-value, which is right here. And then because the differences were normal, then I'm really comparing the means. And we found that the mean of RStudio was in fact significantly greater than the mean of Excel. Now, if we had found, when we were at this point, if we found that the normality was, the difference between the normality was not normal, then we would have gone to the Wilcoxon sign rank test. Okay, and then we would have been comparing the median differences, okay, not the mean differences. So our hypothesis would not look like mu of differences, it would look like median. So here mu with a tilde on top of differences. And how would you have done that in R? Well, when you did t.test, you did the first group, the second group, the sign, paired. When you want a non-parametric test, because you don't have normality, same idea. First group, second group, sign, the number in the hypothesis, and then make sure to say paired is equal to true. When you say paired is equal to true, you'll get the Wilcoxon sign rank test. When you say paired is equal to false, you'll get the Mann-Whitney test. So we want a paired situation. So we're going to say paired is equal to true. And then the other thing that you need to do in this course is to make sure that the exact method is actually turned off. So turn the exact method off. So if you were to run the non-parametric version of a paired test, then here you would get the test statistic to be 168 and the p-value to be 0.009. Okay, good luck.